In this lesson, we'll continue with the precise definition of a limit, as well as carefully define the epsilon delta definition. Again, the idea behind this definition is to bring more precision to this statement. That is, if you have a function approaching a limit, well, how close to this value a do you need to be within some distance of the limit L? In example 1, for epsilon equal to 1, I want to find the largest delta such that this condition holds. This condition says if you pick a distance around the limit, how close to 1 do you have to be equal to? So just to be clear, I want to label all of the stuff in this statement over here. For example, this part means we're approaching 1. So this 1 must be the value of a. Let's label it. That's a. The limit that we're approaching is going to be this value here, which is 5. So this 5 is the limit. The function f of x is this 5x here. So this thing is f of x. And really what this question is asking us to consider is, what is the limit as x approaches 1 of the function 5x equal to? And it should be that it's 5. Going back to the example, I'm choosing epsilon equal to 1. So that's this number here. I'll put that this is equal to 1. Here's what we're looking for. The limit is 5. We're saying put a distance of 1 around 5. How close to 1 do you have to be so all the x values around 1 get mapped to the y values around 5? And visually, it'll look like this. So the epsilon is 1, and that means we go up 1 and down 1 around the limit. And then we have to go some distance around 1 down here, and that distance is delta. So that's what this problem is looking for. Find the delta so all this stuff in here gets mapped up to all this stuff in here. A simple way to find this is by taking 5x minus 5 and setting it less than 1. And trying to figure out, well, what does that mean about x minus 1? What number must it be less than? If you look inside the absolute value, you can factor a 5 out from both terms. It still is less than 1. We can now take the absolute value of 5, which is 5, and we're left with the absolute value of x minus 1, which is simply the absolute value of x minus 1. So we get this. And if you're looking to solve for this, you can divide 5 to the other side of this inequality. So that is x minus 1 absolute value is less than a fifth. And this is the delta that we're looking for. So you can go a distance of 1/5 on both sides of 1. And if you do that, all those x values are going to be a distance of 1 from the limit 5. So I'll write down that the largest delta is equal to, you could say a fifth, or actually you could say 0.2, both are fine. And that means if you're at 1 and you go a fifth in this direction, I'll write this number here as 1.2. And if I go to the left, that's going to be 0.8. So those are those spots here and here. It's the largest one that works because if you pick one that's smaller, so maybe a distance of 0.1 on both sides of 1, that delta will work too because all those numbers are still mapped within a distance of 1 from 5. It just so happens that this is the biggest one that works. Now let's take a second look at the previous example. The only difference is going to be, instead of letting epsilon equal 1, I'm going to say epsilon could be any positive number. Before doing this, I'm going to state the actual definition, the precise definition of a limit using epsilons and deltas. It's a lengthy definition, but here it is. For all epsilon greater than 0, there is, or you can find, a delta greater than 0, such that if 0 is less than x minus a is less than the delta you found, then it must be that f of x minus the limit is less than epsilon. So if you see this statement, it actually is the same thing as saying this whole thing here. Let's try it out in example 2. I'm going to put a distance of epsilon around the limit 5, and I want to find the corresponding distance I have to go around 1, so everything in here will get mapped to everything in here. Visually, it'll look something like this. I'm picking some positive distance around 5. It hits the graph and it goes down to the x-axis like this. So the for all epsilon greater than 0 part is saying the limit's 5 and you're going up epsilon and down epsilon. So you're going a distance of epsilon around 5. What you then have to do is find this delta around this number so that everything around 1 will be mapped to stuff around 5. Using the same technique in the last example, I'm going to take 5x minus 5, and I'm going to set it less than epsilon. I can still factor out 5 from both terms. I'm going to take the absolute value of both 5 and x minus 1. The absolute value of 5 times the absolute value of x minus 1 is what it reduces to. Last time we just simply said, well, the absolute value of 5 is 5, but I have to leave this part as the absolute value of x minus 1. You then divide both sides by 5, and you have that x minus 1 must be less than epsilon over 5. Here I have the x minus 1. Therefore, this thing right here must be the delta, the largest delta. So the largest delta is epsilon over 5. A couple of things to point out. You have to use a positive distance, and it must be that your delta is also positive. Well, if this is a positive number, then so is epsilon over 5. So it's definitely the case that it's positive. And maybe the second thing to point out is here we just have the absolute value of x minus 1 is less than epsilon over 5. But I don't have this. I don't have that it's greater than 0. Technically, in a limit, you don't want to use the number itself. Like, you don't actually want to use 1 in this case. In this example, it doesn't matter, and that's because the number 1 actually does get mapped to the limit. Sometimes it might be somewhere else, but that's not in this case. You can still add in this condition. You can just place this in here and everything still works. But for this problem, it really does not matter. In either case, this is still the largest delta we're looking for. In example 3, I want to prove this statement about limits, but I want to do it by using the epsilon delta definition. So here's what that will look like. We're going to start by saying, well, I have to choose some epsilon greater than 0. So I'll say, given epsilon greater than 0, we need to find, or I'll just put, we need a delta that's greater than 0, such that if 0 is less than the absolute value of x minus 4 is less than delta, then we have the function, which is 7x minus 1 minus 27 is less than epsilon. So that's what we're looking to do. All right, so next what I'm going to do is I'm going to say, all right, but if you look at the absolute value of 7x minus 1 minus 27, we can simplify this. This is equal to 7x minus 28. And of course, we can factor out a 7, and we're left with x minus 4, which is good. I'm looking for an x minus 4. And I can break this into 7 times the absolute value of x minus 4. This is the thing that I want less than epsilon. But, that's the same thing as saying if you divide both sides by 7, that x minus 4 is less than epsilon over 7. So if we choose delta equal to this thing here, which is epsilon over 7, then we know it all works. That is, then if 0 is less than x minus 4 is less than delta, we have that 7x minus 1 minus 27 must be less than epsilon. At this point, this actually proves this proves the limit as x approaches 4 of 7x minus 1 is 27. And the reason is we found some delta distance around 4 such that all of the y values are some epsilon distance around 27. In example 4, we will prove this limit by using the epsilon delta definition of a limit. So to start, I'll say, given epsilon greater than 0, we need a delta greater than 0 such that if 0 is less than, in this case, it will be x minus 1 is less than delta, then the function, which is 1 plus 2x over 3 minus 1, is less than epsilon. So here we're approaching 1, so we're putting a distance around 1. And over here, the limit is also 1, and this is the function. Okay, with all of this, I'm now going to simplify this expression. I should somehow see an x minus 1 and something I can choose as delta. So I'll say, but if you look at the absolute value of 1 plus 2x over 3 minus 1, this is equal to, okay, we'll get a common denominator. It says 1 plus 2x over 3, and I'll say minus 3 over 3, which gives us, if we subtract these two fractions, I have 3 as my common denominator. I have 1 minus 3, which is negative 2, and a plus 2x. So again, that came from, we have 1 minus 3, negative 2, and a plus 2x. Now I see I can factor out a 2 from both terms in the numerator. In fact, you can factor out a negative 2, and that's what I'll do next. So we have, okay, that's negative 2 times, I'll write this as x minus 1. It's really negative 1 plus x, but I'm writing it this way so I can get something that looks exactly like this. I'm still dividing by 3. And this is really the same thing as negative 2/3 times x minus 1. So just to go back, I factored out a negative 2 from both terms. I had a negative 1 and a positive x, so negative 1 plus x. I chose to write that with x first and the negative 1 second. Here I can take the absolute value of negative 2/3 and x minus 1. It'll cancel the negative and give us positive 2/3. But the x minus 1 remains an absolute value. I want this to be less than epsilon. That's because I want this to be less than epsilon, and these two things are equal. Well, if we solve this for x minus 1, I'll put that over here, we get that x minus 1 is less than 3/2 epsilon. So I'm multiplying both sides of this inequality by 3/2 to get this by itself. So I'll make a note that here, I'm going to multiply by 3/2. We found our delta. Since this is x minus 1, this is that largest delta that we need. So if we choose delta equal to 3/2 epsilon, then it must be that if 0 is less than x minus 1 is less than delta, we have the absolute value of 1 plus 2x divided by 3 minus 1 is less than epsilon. This proves that the limit as x approaches 1 of 1 plus 2x over 3 is in fact equal to 1. In example 5, I'm going to use a graphing calculator to find some number delta so that if we're a distance of delta around pi over 4, will be a distance of 0.2 around 1 on the function tangent. So what does that look like? Since epsilon is equal to 0.2, that means I'm going to go up 0.2 and down 0.2 from 1. So I'll draw a number in like this, and a number in like this. So here, this larger number is 1.2, and the lower one is 0.8. Again, those come from taking the limit, which is 1, and going up and down 0.2. Our goal is to figure out, well, what's this x value, and what's this x value? I can use it to figure out how far we are from pi over 4, which is the middle of this interval. So how do we find those x values? And this is where the graphing calculator comes in. What I'm going to do is graph tangent, and I'm first going to graph the horizontal line 1.2, and I'm going to try to use that to figure out approximately this x value of where these two things intersect. So in my graphing calculator, I want to make sure that I'm using radians. So make sure you're in radian mode. But in place of y1, I'm going to put tangent of x. And first, in place of y2, I'm going to put 1.2. Here's what the process is like in my calculator. I graphed it, and I can see tangent, and I can see 1.2, and I can see where they meet. I'm going to press, let's see, I use second and hit the trace button, which is going into calc, and I select the fifth option, and that option is intersect. It takes me back to this graph, and it asks first curve, and I'm going to move the cursor over until I'm close to the intersection point. So I'm just going to push over to the right until I'm reasonably close, and then I hit enter. It then says, okay, second curve, and you just hit enter again. It asks for a guess, and again, I'm just going to hit enter. And it says, for this first one, the x value is, okay, that's 0.87605,805, and that's a little bit past pi over 4, which, by the way, pi over 4 is approximately 0.7853981634. All right, I can now figure out this distance here, and that potentially could be the number delta. But I also need to find this distance here, because depending on which one is smaller, that's the one I want to choose. So I now repeat this process. This time, I'm just going to switch y2. I'm going to make it equal to 0.8 and do this process again. So I'm typing in 0.8 in place of y2, and I hit graph. It's graphing the equation. And again, I'm going to press second and then hit calc. I'm going to choose the fifth option, which is intersect. Okay, so it still says first curve, and I'm going to move the cursor over until we're pretty close to this spot here, and I'm going to hit enter. It says second curve, and so I'm just going to hit enter again. Guess, I'll hit enter one more time, and it gives me that this value here is 0.67474094. Okay, so here are my choices of delta. The question now is, well, what can delta be equal to? And we have two choices. It's either this minus this, or this minus this, and I'll choose the smaller of the two. So first, I'm going to subtract these two x values. I'm going to do, all right, it could be 0.8760, I'll round and I'll say 6, minus 0.785398. And when I type that into my calculator, 87606 minus 0.785398. I get 0.090662. The other possibility is, well, maybe it's pi over 4, which is 0.785398, and I'll subtract off 0.67474094. 0.474. And if I type that into my calculator, 785,398 minus 0.67474, I get 0.110658. We're going to choose this as our delta. The reason you want to choose the smaller of the two is because if you choose the larger and you go the same distance in both directions, you're going to be outside of the interval to ensure that the numbers fall within a distance of 0.2 from 1. So the choice here for delta is the smaller of the two. And since we're asked just to find a number that works, I'm going to take this number and round it to 4 places, but I'm going to round down. So I'll do 0.0906. And if I'm that distance around pi over 4, then all of these x values will be a distance of 0.2 around 1.